Good day everyone, welcome to this video. In this video I'm going to show you how to code a PWM routine in PIC18 microcontroller in assembly, specifically the PIC18 F45K22 microcontroller. And to begin, and I'm going to start. So this is the start of the code as usual. Title, list, include the configuration bits using an internal oscillator. Watchdog time is off. MCLRE, external MCLR. RE3 input pin in disabled, which is the pin where the MCLR pin is connected to, and the low voltage programming is on. So, and the C block, down to the C block, the left duty and right duty. And this particular part, the ISR part is not necessary, but it's really not doing anything, so I'm just gonna leave it in there anyway. And the left duty and right duty is necessary for the duty ratio. And so this is the schematic, not say schematic, the simulation schematic, I guess, of what's going to be used to test the code, essentially. So what you have are PWM pairs here. So the first pair is P1A and P1B, and the second one is P2A and P2B, and it's being used to drive this particular motor, two motors actually, two motors, and P1A and P1B. So in the perfect scenario, what you'd actually have is, let me not say perfect scenario, just an example of essentially how this driver works. So let's say we weren't using PWM, we were just driving directly. So let's say you had a 1 on this pin and a 0 on this pin. The DC motor will spin in a certain direction. And let's say you had a 1 instead on this pin and a 0 on this pin. Then it will spin the other way. The DC motor will actually spin the other way. And it goes the same for this pair as well. And that's the output there. And well, what we're driving with here is actually maximum of 5 volts for this particular microcontroller, but as it goes to the other side, it's actually going to drive the motor with something closer to 12 volts. Alright, and enable, this is the enable part, that's 5 volts, 5 VDD connected to the enable pins, and that's what we have there. And yeah, so this is just an example of how things would be for the microcontroller, to test the code with. And now for the main part, which is the PWM. So essentially what the PWM does is it modulates power for, in this particular case, a DC motor. It could be used for other applications, but I'm not going to get into it. We're just going to focus on the DC motor part here. So in essence, what the microcontroller does is this. The microcontroller has a timer that counts. It counts from here, from 0, counts all the way up to 256, and then it it rolls over, it goes to 0, and then it counts up again. So essentially we have a register, the compare register, and that's represented by this line over here. And what the microcontroller does is it compares what's the value in the compare register to what's the timer, or what the timer is doing at the particular point in time. So in this case here, so when it's here, the compare value is actually higher than the timer value, the count, and at that point the output of the pin is going to be high, and at the point at which the counter value of the timer is higher than that of the compare value, it's going to be low. So it's going to be low over there, and so forth, and etc. And that's how it's going to be. And keep in mind, let's just say, for example, this high value here is represented by 12 volts, right? Imagine this is a 60% duty cycle, like it's on 60% of the time. So let's say this value is 12 volts. So the end result will be a voltage, an average voltage seen by the DC motor of, the average voltage will be 6 volts for the DC motor. That's what we get in the end. And then the whole point of doing a PWM is essentially to get a lower voltage, lower average voltage to the motor than the maximum, because if it's the maximum, then the motor's kind of spinning out of control. But if you can reduce that voltage and make it reduce the average voltage, then the motor, the speed wouldn't be as high. So let's say for a 50% duty cycle, you might get well, you would get an average of 6 volts in this case. But let's say the maximum RPM of the motor is what, 1000 RPM. Then for a 60% duty cycle, it might be 600 RPM. Not necessarily 600 RPM, because it's not linear. I don't think most of the DC motors are linear, so you might get maybe 500 RPM something, but definitely less than 1000 RPM. So that's the use of PWM. And in the microcontroller, this is what's happening in the microcontroller. Let me just explain it one more time. So microcontroller, you have a counter, which is represented by this triangle, and the counter is essentially the timer just counting 1, 2, 3, and so forth. Counts all the way up to, because this is an 8-bit microcontroller, depending on how you set up your timer to work in 8-bit or 16-bit mode. Most of the time, the timers required for PWM in the microcontroller are operating in 8-bit mode, so it's fair to say this is actually 255. So once it gets to the value of 255, well, 255 meaning 2 to the power 8 minus 1. So it goes from 0 to 255, goes back to 0, then all the way up to 255 again. And now what the microcontroller is doing is it's actually comparing that value to a constant value. Think of it as a compare value. So this line, I think I should do it in another color. Yes. So it's comparing the black. Okay, that's not straight. So it's comparing the black line to the red line, right? It's comparing that to the red line. So every time the red line is above the black line being the timer count, there's going to be high. There's going to be high on the particular PWM pin. It's not going to be 12 volts, it's going to be 5 volts. I put the 12 here to represent what it will actually be on the DC motor side, because remember, we have a motor driver here. So 5 volts on this side would represent 12 volts. A high of 5 here would be a high of 12 on the other side. So we have 2 power supplies there. Alright, let's get back to it. Diagram. Alright, so this green part here, that's when the red is above the counter value, the red being the compare value, right? So and at that point it's going to be high, and at the point at which the counter value is higher than the compare value, which is the red value, it's going to be low, and etc, and etc, and it's going to be like that always. also this part is green, that area there, it's going to be high, etc., and so forth. And this particular triangle determines the frequency of this triangular wave or sawtooth wave is going to be, the frequency of the sawtooth wave is going to be directly proportional to the frequency of the PWM signal, obviously. So essentially what we're doing in microcontroller in assembly wise is we're setting up the timer first, setting up the timer frequency. It's in essence setting up the PWM frequency, and we're also setting up the cap, the ceiling for this compare value. So the compare value is CCP XRL. So we're setting up the maximum for CCP XRL, and that value is actually in the PR2 register. So you can directly find get the duty cycle that you actually want from that. So X in this example will be CCP XRL, and PR2 that would be the maximum value that this compare value could be, and then multiply by 100, and we're able to get the duty cycle. So let's say you wanted the duty cycle of 40%, for instance. You put a 40 there, and then you work backwards and you get an X value, and then that would determine what the CCP XRL value should be for a particular duty cycle that you want. And so you set that up for the timer, and then afterwards you have to set up the compare. So this compare, this right here, there's a all different module for it. It's called the ECCP module in the microcontroller that has to be set up. So essentially you're setting up the timer. So first off, you have to set up the ports, because the ports could act as a digital output or analog input. So you need to set that up properly. Then afterwards you set up the timer, and then next you set up the ECCP module, and then after that you can just do PWM, call the functions as you wish, etc. That's an overview of what it is, I guess, theory wise. But that's a very summarized overview. And so yeah, this is code. The OS oscillator in it, 4 megahertz, PWM port in it. Again, I'm not show that yet because it's kind of confusing, not knowing exactly. So next, the timer to initialize. So first off, what you want to do, like I said, the PR2 determines PR2 register PRX, but in this case we're using timer 2, so it's going to be PR2, and this formula is required. So you know this formula should be used to actually determine the PR2 value. So in this case, the frequency of the PWM is actually 1 kilohertz. 1 kilohertz with pre-scale of 4. And this is actually for the timer. Pre-scale of 4 is for the timer. Let me just, it's a 1 kilohertz. And well, actually I should leave that there. Well, it's needed for this particular formula, and this equation is equation 14.1 in the data sheet. 14.1 in the data sheet, and that's where you're gonna find that equation 14.1, and you find the subject of the formula, which is PR2, and this is the equation you get. And obviously the frequency of the oscillator 4 megahertz, PWM frequency required 1 kilohertz, prescale 4, prescale of 4. And there you go for the T2 con, timer 2 con. And in this case it's actually, so this bit here is to turn on the timer, and 01 is signifying a prescale of 4. Just go to T2 con over there, register definition, there you go. And in this case for PWM, the pulse scaler does not matter. So as you can see, everything is zeroed out there. 1 pulse scaler doesn't matter. Pulse scaler is more necessary for when you're using timer interrupts than for anything else. In this case, it's not necessary, it has no effect. And obviously timer X is on, timer 2 turn it on, and the prescale is 4. Obviously the prescale is required because sometimes when you use this particular formula here, you might get a PR2 value that's just way too high. It might be 1,000 sometimes, so you need to actually include a prescale there, to actually reduce that value. And that's that. And now for the EPWM to actually initialize this part here. So there are actually 4 registers that are required for that. The first one is CCP1 con, and just go straight there in the ECCP module. CCP1 con, and here in this stage was actually selected was 0001 0001. So we're in full bridge mode, full bridge output mode. And one was not focused too much on this. Full bridge output mode. So it's 00. So it says here, single output, PXA modulated, PXB assigned as port pins. And here, what is actually important is the choices 1100, 1100, which is here, because we're in full bridge mode. So it's PWM mode, PXA, PXC, active high, PXB. So everything is active. It's all active high. And that's all you need to know about that. This part is pretty confusing to me sometimes, to be honest. But I find that using settings, setting it up to be active high usually does the trick. Right, and the next part, let's put it back there, is yeah, to be honest, this part's not necessary. And next, PWM1 con. Also, I think this you could just ignore for now. That was just something I just put in there to just make sure that yeah, that it ran properly. Because when you use a code generator for the C code, the code generator does not exist for the ASM version, but it exists for the C code. When you use a code generator, it actually generates these guys. I'm not very familiar with them, but I just put them there just to be safe. And this right here is the most important one. It's pulse steering. So if you look here, remember before I said you can have this to be 1 and this to be 0 and this to be 1 and this would be 0. But in this case we're using PWM signals, so what would actually have in this case would have a PWM signal on one and a 0 on the other one. But how do we determine that? Well, we have to use the pulse steering register, the PSTR1 control register, to determine, okay, now this pin, let me go here in my controller, so it's in pairs, so it's P1A and P1B. So in this particular scenario, we want to say this should be a digital output and we want to write the 0 to it. and then P1A should have PWM, or the other way around. This should be a digital output of 0 and P1B should have PWM. That's what the pulse steering is required for. So if I go to that register PSTR1 con, so in this case the Satan, this is the Satan in this case, PSTR1 con, and that's a 1 there. So in the last bit it means PXA pin has the PWM waveform with polarity control from ECCP. So what that means is P1A has PWM in this particular situation, but if this particular bit was 0, then P1A would not have PWM. It will be assigned as a strict digital output, so which means the user, whoever's coding it, would be able to just write just a 1 or a 0 to it. Alright, or in this case we're writing a 0 to it, but if it was 1, there'll be a PWM signal on the particular pin. It's gonna make sense, much more sense in a minute. And lastly we have this register called the CCP TMRS0. Call the CCP TMRS0, and C1, and essentially what that does is so just not get sidetracked. Okay, so from this diagram, so the compare has to be attached to a certain timer for this whole system to work. So to do that, we actually need this register to assign the CCP, the capture compare PWM module, to a particular timer. And in this case, we're attaching it to timer 2. So which means we have to clear these 2 bits. As you can see, we could attach it to timer 4, timer 6. We're attaching it to timer 2 in this case, so these 2 bits have to be cleared, and that's what this is for. So I'm selecting timer 2, essentially. That's what we're doing. And here the CCP-R1L, that's for the compare. That's for the compare value, which must be a fraction of PR2, depending on the duty cycle that you actually want. And now, and also there's a part here that might be a little bit confusing. So for CCP1, in terms of the pins that are assigned to it, just go there. Okay, so to find out what the pins are that are associated with CCP1 and CCP2, you have to go to table 3, and under table 3 this is where you have that you have P1, so you have here, let me just find it, CCP2, you have CCP1, and you would notice that CCP2 is also up here. This is where you try not to be confused, because this is kind of confusing. So keep in mind that by default, when when you initialize everything, it's actually P2A is assigned to RC1, P1A is assigned to RC2, and P1B is RD5, and P2B is RD2. If you look carefully, you're probably gonna find that P2A is also attached to RB3, but you have to set that up specially. That's not by default. That's not the case by default. By default, it's RC1 P2A, as is in this particular diagram here. So let me just do this. Yeah. So it's P2A, RC1, P1A, RC2, P2B, RD2, P1B, RD5. Yeah. That's how it is. And yeah, I think this is the only one of the few times that looking at this table is actually kind of confusing. Anyway, so knowing that, now we could go to the PWM port init. Now the PWM port init actually makes sense. So first off, what you want to do is you want to disable analog functionality on the pins. Well, you have to go back to table 3, and it's not confusing this time. Well, not to me at least. Let's just say P1A. So P1A, let's say P1A would go to AN14. So AN14 is tied to P1A. So essentially, you have to disable analog functionality for RC. For RC2, yes, for RC2 you have to disable analog functionality. AN14, you have to do that for AN25 and AN22 as well. And obviously that's RD2 and RD5, so it's obviously under unsol D, and so forth. And that's that. And then afterwards you just set them up all as digital outputs, and here shows what they're assigned to: P1A, P1B, P2A, P2B. And that in essence is what it is. And now you just go to the main function. Where's the main function say? So essentially what's happening here is we're moving 200 to a register called left duty, and then we're calling this left polarity function. And what the left polarity function does is it enables PWM on one of the pins and writes a 0 to the other pin to make it spin in a certain polarity, just to spin in a certain direction. So you go up here and you can see PSTR1 con. Let me just go back there, and if we go to the, just want to find PSTR. So here is, sorry, bit 1. In this case, bit 1. So you can see bit 1 is set, so which means in this particular situation, P1B is going to have a PWM. It's going to have a PWM signal on it. So P1B will have a PWM signal on it, and P1A will be assigned to a digital output, which will be 0. And P1B is on RD5. Go back here. P1B is on RD5, and P1A is on RC2. So as you can see here, set it up, reset it as a digital output, RC2 that is, and write a 0 to it. And then RD5, you set it up as a digital output, and you write the value what was in left duty, which was 200. You write that to the compare value, and that's how you set up the PWM. I mean, this all seems like a complicated process first time looking at it, but for the first time it looks like that. But yeah, it's just I guess a bit easier way to follow, I guess. And obviously when you're coding it, you know, you might not write it like this. You probably just skip a couple of steps, you know, and be more get more creative with how you decide to apply it in your application, you know. But this particular it's more of a step by step to sort of show how we go from stage to stage, essentially. This is not necessarily showing you how it must be done each time, because, you know, this seems very cumbersome. Let me just explain again. So first, in the particular left polarity, so this right here determines the polarity. There's two lines here. The pulse here in PSTR1 con. So PSTR1 con determines the polarity. So what you have is here PWM on one of the pins, digital output on the other one. So this is a PWM, you have PWM, and you have a digital output on the other one, and then it spins a certain way, it spins a certain direction. And this right here is essentially to make sure that everything is a digital output, and here is to actually how do you say, is for the duty cycle. And if you look at, so this is left polarity 2, if you look at left polarity 1, it's essentially the same thing, 100% the same, except these two lines here, and that's changing the polarity. So now if you look in the data sheet, now instead of P1B to be active, now it's assigned to a port pin, and now P1A is active, which is 1 there, 1 on bit 0. Let's go back there, 1 on a bit 0. And also you have to change the pins, the output pins accordingly. You have to write a 0 to the pin that's not output in PWM, just to make sure a 0, and the other one just a digital output, and obviously set up the PWM. Set up duty cycle, and that's that. And the exact same thing for the right polarity. Obviously this time it's going to be PSTR2 con instead of PSTR1 con, but everything in this essentially stays the same. And I encourage you to just take a look at it, take a look and play with it, experiment with it, you know, turn it upside down, and just, you know, try to see, you know, you might even want to delete some lines, see what's necessary, what's not necessarily necessary. I didn't do that on purpose. You just want to find out exactly what works and what doesn't. Alright, so now for the demonstration. So I'm just running this, and obviously here I'm running both of them in polarity 2, left polarity 2 and right polarity 2. Just run it. You can see it's spinning one way, and now I stop that and I change them to polarity 1. Run it, compile rather. Alright, let me just go back. Now gonna, they're both spinning the other way. And obviously it's spinning at a certain speed. Let's say we wanted to go slower, just change that to let's say 100. Let's make it 100. Remember, the maximum is 249, so right now it's about I guess less than 50% duty cycle, so it should be not as fast as it looked before. And as you can see, it's much slower, and that's in essence the whole point of PWM. And if you look here, you can see one has a PWM signal, the other one has a 0. Look here, one has a PWM, the other one has a 0. And that in essence is the whole point of the PWM. So we could modulate the voltage, in essence modulate the power, and subsequently modulate the speed. And obviously you can have them flow spin in two different directions, left polarity 1, right polarity 2. And as you can see, they spin in opposite directions. So yeah, so that's PWM essentially. The one thing to keep in mind is you just have a general picture of what a PWM is, which is this. Looks very awful, but hopefully it made sense. This is just a general idea of what PWM is. You have the sawtooth wave at a certain frequency determined by the timer and the PR2 register, and then you have the compare value whose maximum is limited by the PR2 as well. So PR2 in essence is sort of like a multi-purpose register in a way, and which is the CCP XRL determines the duty ratio, and just using this as a guide to essentially initialize. And I guess the most confusing part of PWM is the pins. The pins. But just remember, by default, these are the pins that are used in full bridge mode. Full bridge mode determined by CCP1 con. CCP1 con register. Let me go back there. CCPX con rather, and that's what's determined by that. As you can see here, active high. It's active high. To be honest, sometimes I don't understand the language that the microcontroller uses. The datasheet uses as active high or not, you know. But anyway, this particular setting usually does the trick for that. And this register determines what has PWM and what has a 0 on the output, and this is for the duty cycle, and this is to select the timer. So if you wanted to select it to another timer, you would go to this register, CCP TMR SO, S0 rather, and you would look at the definition there. Where is it? There. As you can see here, there's one for CCP1, CCP2, there's one for CCP3, and CCP4 and CCP5. And there you go. And that in a nutshell is PWM. I hope this has made sense, and I wish you the very best of luck with your trying out of this, with trying this out in the real world. Well, alright, that's it. Thanks for watching. If you've got any questions, you could just serious questions, you could just ask and try to answer them. Alright.